everyone. Let's see. We got another group theoretic result to prove, and so this one, this is lemma should be 6.9, and it goes like this. So if we have a set that has prime cardinality, so let's say if the cardinality of X is prime, and G acts faithfully and transitively on X, and G contains, well, it's really the image of G, I guess. And let me just say, I'll put it in parentheses here, the image of G contains a transposition then G is equal to S sub X, so the entire permutation group of the set X. So, I mean, this is one. The idea of group actions, right, is a huge and important area of group theory, and what it allows you to do is to get information about the group by seeing how it behaves, how the action of G behaves. And so here's an example, right? If we know that we have a faithful and transitive action, and G contains a transposition, then just by knowing the order, or I should say the order, the cardinality of the set, right, we can conclude that G is equal to the entire permutation group. Okay, so let's say it like this. Oh, and I mean, I put this in quotes, or in parentheses. I mean, you want to be able to go back and forth between G as an abstract group and G viewed as a subgroup of the permutation group under the action. Remember, an action is a homomorphism from G into the permutation group, which means that when it's faithful, right, you can view G as a subgroup of S of X, right? So I put it in parentheses here, and I'm just going to treat G, in fact, notice here I wrote G equals rather than isomorphic to, right, because we're identifying G with its image within S of X. So since G contains a transposition, there exist X and Y in X such that X is equivalent to Y. Remember the equivalence relation that we had from our previous result, and so the cardinality of the equivalence class of X is strictly greater than 1, right? It's got at least one other element within the equivalence class, right, namely Y. Now, if you remember in our last result, that was lemma 6.8, when we have a faithful and transitive action, the set of equivalence classes, or each equivalence class, has the same cardinality, right? So by lemma 6.8, every equivalence class has cardinality greater than 1, right? They've all got to have the same cardinality as the equivalence class of X. Now, we know that the cardinality of X is prime, so let's write that as a little p. So let's write cardinality of X equal to p, where p is prime. And let x1 up through xn in capital X be such that X is equal to the union I equals 1 to n equivalence class of X sub I, and, or let's say where, X sub I equivalence class intersect X sub j equivalence class is empty when I not equal to j. What are we saying here? We know that the set of equivalence classes forms a partition of the set X, and so we're just writing that out, right? The partition means that X is equal to the union of some disjoint collection of equivalence classes, right? So we're just choosing the X sub i's that make that happen. Now, okay, so then, P is equal to, well, it's equal to the cardinality of X, which is equal to the sum, I equals 1 to n, of the cardinalities of each of the equivalence classes. But each of the equivalence classes from our previous lemma 6.8, each of these equivalence classes has the same size. So this is equal to n times, I think I just wanted to use x sub 1. Yeah, x sub 1. N times the cardinality of the equivalence class x sub 1. Now, we know that P is prime. We know that the cardinality of this equivalence class is greater than 1, which forces, right, because P doesn't have any factors other than P and 1 itself, it forces n to be equal to 1, and that then tells us that this number right here has to be P, right? So it follows that n equals 1, and so, well, okay, so if the size of this equivalence class is equal to P, that means that the equivalence class itself has to equal X. So the equivalence class of X sub 1 is equal to capital X. Okay, so now, we can say, given any little y in, well, I don't want it to be x1, so this would be in capital X minus x1. So any element of x that's not equal to x1, we know, right, because the equivalence class of x1 equals all of x, that means that y has to be equivalent to x1. So we have x1 tilde y, and so the transposition x1, do I want x1 first? Yeah, x1 comma y is an element of capital G. So now, let's take any element. Now, given any y and z in capital X, we have y, z, the permutation, equal to, I'm going to write it as x1y times x1z times x1y. Now, we know that all the permutations of the form x1 comma whatever live in G, so this product is in G. And so what that tells us then is that every transposition lives in G. So therefore, G contains all transpositions. All right, so every transposition lives in G. And then you have to remember back to math 481, right? S sub x, the group of permutations, is generated by its transpositions. So since since S of x is generated by its set of transpositions, we see that G is equal to S of x, right? If all the transpositions are sitting inside G, right, that means that it generates, it fills out the entire group. All right, now we've got one more result left, and then we'll be able to actually produce a polynomial that is not solvable by radicals. And so this is the last piece of the puzzle right here. So this would be theorem 6.10. So let's let f in q bracket x be irreducible over q with degree equal to the prime p, right? So we have an irreducible polynomial with degree p where p is prime. If f has p minus 2 real roots and 2 complex roots, then the Galois group of f, right, that's going to be isomorphic to, or equal to, let's say, is isomorphic to, is isomorphic to S sub p, the symmetric group on p numbers. Okay, so let's see, we need a splitting field here, so let's let sigma be the splitting field, so let's let q contained in sigma, contained in, or do I want this to be just in C, right? C, be the splitting field for f over q. Now, since f is irreducible, over q, we know that the Galois group, so gamma of f, acts faithfully and transitively, on the set of roots of f, so on the set capital R of the set R of roots of f. And I don't know why I didn't write down the theorem number there, but it's from a theorem from the past. And right here, what that means is, right, so we can think of it this way. So gamma of f, we can then view as a subgroup of the symmetric group, right, the group of permutations of the set of roots R. Let's say like that. Now, so we know that we've got exactly two complex roots. So the complex roots of f are of the form. So remember that the complex roots of a polynomial come in complex conjugate pairs. And so let's write them so they are of the form a plus or minus bi for some real numbers a and b. And so the mapping, let's call it tau, from C to C, defined by oh, well, do I want to say that way? Yeah, that's fine. So I want to take, so tau of x plus yi. So here's an arbitrary complex numbers. Here I want these a and b. This is the set of roots. So a and b are constants here. They're fixed. So defined by t, or tau of x plus yi, equal to x minus yi, is an automorphism of C that fixes Q. So this is that. That fixes Q. In fact, it really fixes all of R, right? Right, all you're doing is tweaking the imaginary part, but the real part of each number stays fixed. So it doesn't matter, but we'll just say in fact tau fixes R. So now note that sigma is equal to Q adjoin the set of roots. And so if we look at tau restricted to sigma, and we apply it to sigma, what's it going to do? Well, okay, so it's going to fix every element of Q. It's either going to fix the root, or it's going to take the positive conjugate, the a plus bi goes to a minus by, and a minus by goes to a plus by. And so this is equal to sigma. Okay, fine. What does that mean? Well, it means then, so thus, tau restricted to sigma, so that's going to be an automorphism of sigma that fixes Q. In other words, it lives in the Galois group. So now, since tau restricted to sigma is a transposition, viewed as an element, as a group of permutations of R, right? It interchanges two of the roots and leaves the other ones fixed, right? That's a transposition. So since tau restricted to sigma is a transposition, and the set of roots is prime, Now we can apply our previous theorem. Gamma of f is equal to S sub r. That's our previous lemma, which is by so lemma 6.9. And so our final conclusion then, because R has p elements, so we can say therefore gamma of f is isomorphic to S sub p. All right. And so now we're ready for an application. The polynomial, let's call it f equals x to the fifth minus 4x plus 2 is not solvable by radicals. So I want to use our previous theorem. All right, let's check out the nature of the roots of this polynomial right here, and if they fit the conditions of our previous theorem, right, then we'll be able to conclude that our polynomial, that our Galois group is isomorphic to S sub 5. All right, and then, well, I don't know why I'm spoiling the punchline here. So here we go. So first of all, this polynomial is irreducible by Eisenstein. So f is irreducible by Eisenstein. Now, you can use the intermediate value theorem. So use the intermediate value theorem to show that f has exactly 3 real roots. Well, I guess at least 3 real roots. I guess. Okay, so it has at least 3 real roots. So this is kind of a Calc 1 exercise. Right, what do we have to do? We just have to show that the polynomial has a positive output followed by a negative output. That tells us then that the polynomial has to cross the axis. A positive followed by negative or vice versa. So what do we have? F of minus 2 is less than 0. F of 0 is positive. F of 1 is negative. And f of 2 is positive, right? So each time we get that should be a 0 there. Each time we get a sign change from positive to negative or negative to positive tells us that we're guaranteed to have a root lying within the interval. So for example, this tells us f has a root in the interval from minus 2 to 0. This tells us that f has a root in the interval from 0 to 1. This tells us f has a root in the interval from 1 to 2. So we know that there's at least 3 real roots. Now, I want to show that it actually has exactly 3 real roots. So now, by Rolle's theorem, each pair of adjacent roots well, what does that tell us? So Rolle's theorem says this: if you've got a continuous function and you have matching output, then it's somewhere in between, continuous and differentiable, somewhere in between, you had to have a horizontal tangent. So each pair of adjacent roots corresponds to a horizontal tangent, which means a root, right? A place where the derivative is 0 So it corresponds to a root of f prime of x, and the derivative here is going to be 5x to the 4th minus 4. Now, this one has exactly 2 real roots, right? So since f prime has exactly 2 real roots, right? I mean, you can basically factor this as something squared plus something, and then minus. I don't want to think about the factorization. Oh, you know, it's square root of 5. X squared plus 2 square root of 5 x squared minus 2. Right? Did I get that right? 5x to the 4th, blah, 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 and then minus 4. Yeah. So there are 2 real roots coming from here. The roots of this part right here are imaginary. So what that tells us then, right, we know that there's exactly 2 real roots, which means that we could not have another pair of adjacent roots. We have 3 pairs of adjacent roots, which tells us now that there are exactly 3 real roots. So since f prime has exactly 2 real roots, we conclude that f has exactly 3 real roots and 2 complex roots. Okay, so the conditions for our previous theorem are now met. So by theorem 6.10, the Galois group of F is isomorphic to S sub 5, which is not solvable, and now it follows directly from, this is theorem 6.7, so by theorem 6.7, F is not solvable by radicals. Right? Because what does the theorem say? If it was solvable by radicals, then its Galois group would have to be solvable. And so, I mean, should we all, you know, have a virtual group hug? We just finished. I don't know what I'm talking about. We just finished a long journey, right? From the beginning to here, right? It's taken us till this instant right now. We now have seen, or we've seen the end of the journey. I can't think of the appropriate big words to say right now. So what do? Right, this was a task that lasted for thousands of years, or we're considering it for 1,000 years, that ended with the work of Galois. We've found that there is no general formula that will allow you to find the roots of every degree 5 or higher polynomial, right? Because here is a polynomial where there is no formula that involves just, if there was a formula out there that involved extracting roots, addition, subtraction, multiplication, and division, and produce roots of polynomials, it would fail on this polynomial right there. Okay, take a deep breath and let's just sort of let this sink in. I can't even come up, I'm just sort of stumbling over my words now to try to describe the magnitude of what we just did, right? We just did it. So, I don't know, clap. Oh.